Welcome everyone, welcome to this session. And in this session, I'm going to discuss about the interference of light, or you can say I'm going to discuss about the second part of interference of light. In interference of light, we have two kinds of phenomena. One is division of wavefront and another is division of amplitude. Division of wavefront is a Young's double slit experiment. We discuss Young's double slit experiment, and whatever we do in that is a wavefront division. So a wavefront coming from one source divides into two different sources, and then they combine together to give you interference pattern. Division of amplitude basically means that some part of the energy gets divided into two parts, and then those two parts interfere with each other and gives you the final pattern. In division of amplitudes, in the previous videos, we already covered the Newton rings. And the Newton rings question was asked in IIT JAM 2024. Today we are going to do is thin films, and thin films questions have been asked in 2023 and many years before that as well. So before I jump into the question, first we will understand the concept of thin films. So the light is coming from air, or you can say some vacuum material, and it enters into some material. So this yellow is your material, and this material has a refractive index n, and the thickness of this material is T. So T is the thickness of the material film. It's a very thin film, and then you have a material N. Is the refractive index of this material is N. So when the light comes, some part of the light, you see, not entire, some part of the light refracts. It enters the medium, and on the other hand, some part reflects. So some part is refracted, and on the other hand, some part is reflected. The light which is refracted, so you see this transmitted light, it again reflects back, and then it again transmits back and give rise to second wave, right? And then wave number 1 and wave number 2 interfere with each other and give rise to the pattern. So basically you see the division of the energy is getting happening. So first division happened here, then second division happened here, and then every time we are getting some sort of division and we are getting a final pattern. The light comes, reflects, and some part transmits, and that transmitted part again comes back. So wave number 1 and wave number 2 interfere with each other and give rise to the interference pattern. And we are interested in what we can derive from all of this. So let's say the refraction angle, this angle is R. So this is what our assumption is. Whenever you want to discuss interference, whenever you want to find out that if you have a maximus or if you have a minimus based on the thickness of the film. So if you change the thickness of the film, either you will get the maximus in the output, or you will get is a minima. Either the lights will interfere with each other and give rise to a very bright light, which is a maxima, or these two light 1 and 2 will interfere with each other and they will actually cancel each other out, and they will give rise to the minimum. So we need to decide what will happen based on the thickness of the film. So let's understand. In order to understand that maxima and minima, we need the path difference between them, or the phase difference between the waves. So what is the path difference between wave 1 and wave 2? So the path difference between both waves, let's say, is given by delta x. Delta x is a path difference between them. The path difference is coming because both of them are covering the different distance. You see, this wave only came till here and then reflects, but the second wave has covered the extra distance, and this extra distance is 2t cos of r. How I am saying that? If you look at this triangle, you can clearly see that this triangle, this thickness is t and this is r. If I take cos of r, I will get base upon hypotenuse, right? And what is hypotenuse? Hypotenuse is AB. So this is A and B. So AB is going out to be T cos R. Okay? AB is T cos R, and AB and BC are both equal. So both of them are T cos R. So the total path difference is going to be 2T cos R. 2T cos R. Okay? That is going to be a total path difference. But since this difference is inside the material, we don't take the actual path difference, we take the path difference, going to be 2 nt cos r. 2 nt cos r. So we multiply by the refractive index n. So that is why you see 2 nt cos r. So this path difference is because of the both of the lights are covering the different distance. So the overall we are getting is 2 nt cos r. Now we will subtract some number which is minus lambda by 2, and this minus lambda by 2 is coming because you see at point B, or sorry, at point A, the reflection is happening from rarer to denser medium. And in the lectures I have already discussed, whenever the light is reflected from rarer to denser medium, outside is rarer and inside is denser, then additional path difference is you have to subtract, which is lambda by 2. So that is why I'm subtracting lambda by 2 here. So this is because of the difference in lengths, and this is because of the reflection from rarer to denser medium. So this is something I need to keep in mind. I need to remember this. What is the path difference in case of thin films? So the path difference is 2 nt cos r minus lambda by 2. If you have a maxima, then this path difference will be m lambda and you will get maxima. And if you have minima, this path difference will be 2m plus 1 lambda by 2. Because whenever the path difference is 0, lambda, 2 lambda, so on, you get a maximum. And whenever the path difference is lambda by 2, 3 lambda by 2, 5 lambda by 2, you get a minimum. Okay? So that is a concept. Clear? Now in our problem, if you look at carefully, in our problem, you see the thickness is given to us, refractive index is given to us, and the light is incident normally. It means the incident angle is 90 degrees, so the reflected angle will also be 90 degrees. So if the light is coming straight away, then I and R both will be 90 degrees. They are asking that which of the light will be predominantly visible. Which light you will see the most? Basically, which color maximas you will see? So you will see some maximas. So you see in a soap bubble, you see a rainbow. So you see only few colors in the soap bubble. So only few colors are visible because only for few colors you have a maxima. For other colors you have a minima. So basically they are asking that for which color you will have maxima. And we have the 4 options in front of us. Right? All of them are between 400 to 650. Okay? So let's see. So we will use this formula. So we will say what is our phase difference or path difference? 2 nt cos r, since this is 90 degree, 0 degree, sorry. Yes, this is 0 degree, not 90. I think I said wrong. For both of them, it is 0 degree. Incident and reflected angle are 0, right? You see how it works. So this is if light is coming like this, the angle with the normal is actually, this is your normal and this is your light. The angle between them is 0 degree. Right. So angles are always taken with the normal, right? These are the angles we always take. So if the light is coming normally, then the angle is actually 0 degree. So cos 0 is 1. So this is gone. So we get 2 nt minus lambda by 2. And in order to get maxima, we get m lambda because we want to see which colors are visible. So we need maximas. So we make it equals to m lambda. So then we get 2 nt equals to m plus half lambda. So m plus half lambda is equals to 2. N is the refractive index and T is the thickness. So if you solve it up, you will get 749.7 nanometer. Okay, it is nanometer. Then we can divide by m plus half. So you can get wavelength, which is 749.7 divided by m plus half. Now you can just keep putting the values of m. If you put m0, you will get this 1499.4. If you put m1, you get 499.8. If you put m2, you get 299.9, and so on. So only this number is within the limits or within the options which are given to us. So 499.8, which is almost 500 nanometer, will be seen very predominantly. So we will see a green color maxima in this film. So when the light will reflect back, we will see the green colored light there, because only for the green color the maxima condition is being satisfied. So the first thing we did is that we found the path difference for this thin film, which is 2 nt cos r minus lambda by 2. The second thing that we did is actually we made this delta x equals to m lambda for maxima, and then we solved and we find the different values of wavelength, and one value was within our options and that was our final answer. So that was about the thin films. I hope you understand this lecture, and there are many other problems which are there in the PYQs, and you can see your DPPs which are available in Physics by Aaryan, IIT JAM, and GateNet course. In that DPP, I have included all the problems of the interference and the thin film, which have been asked in the previous course. So now I will see you all in the next lecture, and that's all for this class.